Hello listeners and viewers. Welcome to Kaduna State Ministry of Education Radio and TV e-learning program designed for our SS3 and other students staying at home due to the coronavirus pandemic. The present administration, under the able leadership of His Excellency, Malam Nasir Ahmed El-Rufai, is positioned as always to ensure that under his leadership, our students are not left behind in all areas of human endeavors, especially education. Kaduna State is the center of learning. Therefore, we want to ensure that our students excel in their forthcoming examinations and beyond. Students and other learners at home are given this opportunity in order to continue learning, as education is a continuous process. Different subjects will be taught in this program to assist students to perform excellently in the forthcoming Senior School Certificate examination being conducted by NECO and WAEC as soon as schools reopen. Teachers making presentations will always provide their names and phone numbers during each presentation, and they can be contacted for questions, further explanations, and/or clarifications. The following numbers and contacts can also be reached for expression of any concern or observation: 090-865-00545 or 080-383-62072. Our website is www.education.kdsg.gov.ng. Our email education@kdsg.gov.ng or education.kdsg@gmail.com. Our YouTube channel, Ministry of Education, Kaduna State. Our Twitter handle @Kaduna_MOE. Or our Facebook page, Ministry of Education, Kaduna State. Stay safe, stay at home, and learn well. Thank you, happy listening, and happy viewing.
Good day, learners at home. Welcome to today's physics lesson on radio, television, e-learning program of Ministry of Education, Kaduna State. My name is Hassan Buki. We are going to continue with our topic, radioactivity. In our last lesson, we treated radioactivity 1. So today, we are going to continue with radioactivity 2. Radioactive decay. Radioactivity is a spontaneous process. It is not affected by external factors such as temperature, pressure, and chemical reaction. Each radioactive element has a definite date of decay, which can be characterized by its half-life. What we are saying here is this: just like we saw in our previous lesson on radioactivity 1, that radioactivity is a spontaneous process. It happens naturally without the influence of any external factor such as temperature, pressure, chemical reaction. It happens on its own, and it has a definite time that this takes place, and it happens periodically, which is referred to as its half-life. We take half-life. Let's go back. So, half-life of a radioactive element is the time taken for half of the atoms initially present in the element to decay. That means that is the time taken for any atom, okay, to decay by half. So we have mathematically, it is given by T half is equals to 0.693 over lambda, where T half is equals to half-life, lambda is equals to decay constant, and lambda, which is decay constant, is defined as number of atoms disintegrated per second, all divided by number of atoms in the source at that time. Decay constant lambda in words is defined as the instantaneous rate of decay per unit atom of a substance. Now here we have our decay curve and half-life. We have on our vertical axis the activity or count rate, and on our horizontal axis we have time in seconds. And this is an exponential curve. Now time t1, okay, shows the time when the atom is n. The original atom is reading n. And t2 shows the time that the original atom n1 has disintegrated or decayed by half. Now, if we want to find the half-life that n1 has disintegrated or decayed to n1 over 2, which is half, it will be t2 minus t1. Then t3 shows the time taken for n1 over 2 to disintegrate or decay by half again, which will now be n1 over 4. And to find the second half-life, it will be t3 minus t2. Now we look at examples. Example number 1 says a radioactive element has a half-life of 3 minutes and its count rate at 0 time is 512, that is 512. At the beginning of the 13th minute, what will the count rate be? That means at the beginning of the 13th minute, what is the count rate? So solution. After 3 minutes, which is the first half-life, because we have been given in the question that the half-life is 3 minutes. So after 3 minutes, which is the first half-life, count rate will be 512 divided by 2, which means 512 has decayed or disintegrated by half, which is 512 divided by 2, and we will have 256. After 6 minutes, which is second half-life, that means after another 3 minutes in the second half-life, which will give us a total time now of 6 minutes. Now count rate will be 256. That means what remains here divided by 2, which means it has disintegrated or decayed by half also, and that will give us 128. Then after 9 minutes, which is the third half-life, our count rate will be equals to, which means this 128 now has again decayed or disintegrated by half. So it will give us 64. That is 128 divided by 2 is equals to 64. After 12 minutes, which is the fourth half-life, our count rate will be equals to 64 divided by 2. And that will give us 32. Now we can see that after 12 minutes, which is the fourth half-life, the count rate is 32, which therefore tells us that at the beginning of the 13th minute, the count rate will be 32, which is the beginning of the fifth half-life. Example 2 and 3. So we take example number 2. It says a radioactive isotope has a decay constant of 10 to the power of minus 5 per second. Calculate its half-life. Solution. From our formula, which we've seen before, that T half, which means half-life, is equal to 0.693 divided by lambda, where lambda is our decay constant. Substituting our values, it will now be equals to 0.693 divided by 10 to the power of minus 5, and which will give us 6.93 times 10 raised to the power 4 seconds. So which means that the half-life of this radioactive isotope is 6.93 times 10 raised to power 4 seconds. Now in exams, most especially like in objectives, this will be expressed in different forms, in different standard forms or decimal fractional forms. Depending on your knowledge of mathematics, you can be able to determine the correct answer. Example number 3. A radioactive sample initially contains N atoms. After 3 half-lives, what will be the number of atoms that have disintegrated? Solution. After first half-life, what remains is equals to N over 2. That means half of it, of the original sample. After second half-life, what remains is equals to N over 2 all divided by 2, which means half of N over 2 has now reduced by half, which will be equals to N over 4. After third half-life, what remains is equals to N over 4 divided by 2, which means half of N over 4 has disintegrated or decayed. And that will be equals to N divided by 8, or N over 8. So, after 3 half-lives, the number of atoms that have disintegrated or decayed will be equals to N, which is the initial sample, minus what remains, which is N over 8. So, when we do our mathematics, N minus N over 8 will give us 7N over 8. Which means, from question 2, which means, from here, which means that what remains, or sorry, what has disintegrated after 3 half-lives is 7N over 8. That is what has disintegrated, and what is remaining is N over 8. Question number 4. A sample of radioactive element with half-life of 2 minutes initially contains 8 times 10 to power 6 atoms. Find the time at which the number of atoms of the original element of the sample is 2 times 10 to power 6. I take the question again. A sample of radioactive element with half-life of 2 minutes initially contains 8 times 10 to power 6 atoms. Find the time at which the number of atoms of the original element of the sample is 2 times 10 to power 6. Solution. Our half-life is given as 2 minutes. Initial amount of atoms is equals to 8 times 10 to power 6 atoms. Now, after 2 minutes, which is first half-life, what remains is equals to 8 times 10 to power 6 divided by 2. And that will give us 4 times 10 to power 6. After 4 minutes, which is the second half-life, what remains will be equals to 4 times 10 to power 6 divided by 2, which means 4 times 10 to power 6, okay? from our first half-life has now reduced by half, and we have 4 times 10 to the power 6 divided by 2, which is equals to 2 times 10 to the power 6. Which means, therefore, that it will take 4 minutes for the sample of the atoms to reduce to 2 times 10 to the power 6. It will take exactly 4 minutes for the sample atoms initially at over 2 times 10 to the power 6 to reduce, it will take 4 minutes for the initial sample 8 times 10 to the power 6 to reduce to 2 times 10 to the power 6. Now, these examples have been taken from past WAEC questions and JAM questions. So you can see that with these examples, you should be able to solve any questions, because the examples have touched all areas that a question can come out in an exam in half-life of an atom. So what you need to do is, apart from the assignment that will be given to you, I advise that look for more questions in your textbooks, in exercises in your textbooks, and past WAEC questions or JAM questions, and attempt them. When you keep doing like this, it is said that practice makes perfect. That is how you will get to master these things, by constant practice. Before I go, I will introduce my colleague that will come and give summary of what we have learned so far, and then go ahead to give you the assignment that will follow. I remain Hassan Buki. Don't forget to stay home, stay safe, and keep learning till we meet in the next lesson. Thank you.
Hello, learners. Good day. I am Napoleon Kure, and I'm here to summarize what my colleague has taught you on Radioactivity 2, that is part 2. As has been said, as a reminder that it is radioactivity, a spontaneous process whereby the nucleus of an atom disintegrates or decay or break down into smaller parts, and a number is affected as initially seen. This activity, as we can see, is not affected by external factors which have been highlighted before now. And what are some of these factors? Pressure, temperature, and chemical reaction. And we see that for any given nucleus of a given element, there is a specific time it takes such a nucleus to decay to have its initial number of particles. And the time it takes for this to happen is referred to as half-life. And that is why we talk of half-life as a radioactivity, of a radioactive element. Is a time taken for half of the atoms initially present in the element to decay. To decay means to reduce, to decrease in number. If you have, for instance, 100 atoms and the time it takes for 50 of the atoms to have reduced or have decayed away, we say that time is referred to as half-life. And there is a relationship that exists between that half-life and the decay constant, as we see. And it is giving us small t subscript half equals 0.693 over lambda. And that t subscript half is what we refer to as half-life. Don't get confused. There could be a different symbol that could be used for half-life. As far as it is defined as half-life, could be capital T, is still the same thing. Our lambda remains our decay constant. And what is decay constant is simply the ratio of the number of atoms disintegrated per second to the number of atoms in the source at that time. So if at a given time you have, let's say, 50 atoms, and within that time you have a number of atoms in every 1 second, such a number, a given number, is reduced. That number divided by that 50 is given as our decay constant. And it can also be defined, our decay constant, apart from the mathematical expression expressed above, it can be defined as the instantaneous rate of decay per unit atom of a substance. There is a curve or a graph that helps to define what we refer to as decay curve and half-life. On the horizontal axis, we have what we call activity or count rate. And on the horizontal, you have the time given in seconds. It could be in minutes. It depends on what unit of time that is expected to be used. The title remains decay curve and half-life. Sorry that we don't have the activity written there, but that is what is expected to be there. And you can see that the curve touches the vertical axis. Anytime you are asked to explain this curve, you are expected to make sure that the curve touches the vertical axis. Otherwise, it does not. That is to tell you that it is from a given value. And with this, you have anytime there is half of the atom decayed, then it will be from N1 to our N1 over 2. If another half of it from that N1 over 2 decay, you will have that N1 over 2 divided by 2, and that will be N1 over 4. Now, on the time axis, the time it exists for the N1 is given as T1. So by the time the number N1 has decayed to half its original, then you will have the time elapsed will be T2 minus T1. If there is a further decay of half of the number at N1 over 2 to N1 over 4, then you will have from T2 to T3, you have another time given. And so T2 minus T1 is half-life, and T3 minus T2 is half-life. Please don't forget that there is a corresponding line drawn to show the N1 and all other axes. And so, from the example given, we have very important, the radioactive element has a half-life of 3 minutes, and the count rate of such is, at the count rate at 0 time is 512. That is the number of atoms, for instance, present originally is 512. If at the beginning of the 13th minute, what would be the count rate of such number? And then when we talk of phase half-life, it just refers to the phase decay. What is a number that half of the atom present to decay up to? And then the second half-life also refers to second decay, third half-life, third decay, fourth half-life, and so on. And by the time it happens, then you will see that you must have arrived at 32 for your value. And just as he has said, we have an assignment. As you go over what my colleague has said, assignment is given to you to help you have a view of what you have learned. On number 1 of the assignment, you have 4 grams of radioactive material of half-life 10 days is spilled on a laboratory floor. How long will it take to disintegrate 3.5 grams of the material? Number 2, Assignment: the half-life of a radioactive element is 9 days. What fraction of atoms has decayed in 36 days? Question 3. If the decay constant of a radioactive substance is 0.231 per second, what is its half-life? I'll go over the assignment again. Number 1, 4 grams of radioactive material of half-life 10 days is spilled on a laboratory floor. How long will it take to disintegrate 3.5 grams of the material? Question 2. The half-life of a radioactive element is 9 days. What fraction of atoms has decayed in 36 days? Question 3. If the decay constant, which is lambda, of a radioactive substance is 0.231 per second, what is its half-life? References are given for more consultation on what has been given. Number 1 reference is New School Physics by M.W. Anyakoha. 2. All-Inclusive Calculations in Physics by Solomon Dauda Yako. 3. Senior Secondary School Physics, that is SSS Physics, by P.N. Okeke and M.W. Anyakoha. Reference 4. Essential Physics for Senior Secondary Schools by O.E. Farinde and H.E. Ehimitalo. The last on the list is Calculations in University Physics by Emeka E. Ike. Our contacts are Hassan Buki 080 65 50 43 46. Napoleon Kure 080 36 36 2105. Please stay at home as you remain safe. Stay safe and keep learning. Good day. Till we meet in our next lesson.